Welcome everyone to this 13th lecture of the states of matter. Myself Varad Daoo. I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. So in the previous class, we have seen about the liquefaction of gas. We have seen about the what are the critical points and the temperature, pressure, and volume at this critical points, and how do these correlate with the van der Waals constant. We are worried. And today's class, we are going to delve into the liquid state of matter, and we are going to study about various properties of liquid state of matter, right? The first topic which we are going to study about today is liquid state of matter. Liquid state of matter. So liquids have a definite volume but not definite shape. These take the shape of the container. In terms of kinetic molecular modeling, the molecules of the liquid are close together and attractive forces between molecules are strong in comparison to gases. Right? The molecules of liquid are close together and attractive forces between the molecules are strong right, in comparison to those in gases, in comparison to those in gases, right? However, the intermolecular forces are not strong enough as in solid to have definite shape, but they cannot be separated from one another completely, and this results in definite volume for liquid. Another important distinction between gases and liquid is the extent of order. In case of gases, there is complete random distribution of gas molecule. This corresponds to disorder state, whereas in case of liquids, there is significantly more order or less disorder, right? But this order is definitely less than that in solids, right? So let us write this down. So another important distinction between liquids and gases, important distinction between liquid and gases is the extent of order. Right? In case of gases, there is complete random distribution of gas molecules, okay? And this corresponds to disordered state, right? In the case of liquids, however, there is significant more order. Or less disorder, right? But this order is significantly less than that in solid. But this disorder is significantly less than that in solids. Right? In order to understand this, let me drag a picture. So this figure right here is representative of the very extent of order for various systems, right? Thus the liquid state, so this here represents the gaseous state where it is completely random, right? Partial order is liquid and complete disorder is gases, right? So this has to be solids, right? Right? So we can see that liquid state is an intermediate between solid state and gaseous state, right? Liquids are neither completely disordered, right? These liquids are neither completely disordered like gases, nor they are completely ordered like solids, right? So now let us understand the kinetic molecular model for liquids. Kinetic molecular model for liquid. Kinetic molecular model for liquid. Right? The first, in terms of kinetic molecular model, the nature of the liquid is described as below. Right? Liquids are composed of molecules. Liquids are composed of molecules. Right? The molecules of the liquid are held together by appreciable intermolecular forces. The molecules of liquid are held together by appreciable intermolecular forces. Right? The third is, due to weak intermolecular forces, the molecules are in constant random motion. Due to weak intermolecular forces, the molecules are in constant random motion. Constant random motion. The fourth one is, the average kinetic energy of molecules in a given sample is proportional to the absolute temperature. The average kinetic energy of molecules in a given sample is proportional to the absolute temperature. Right? Absolute temperature. It may be noted that the nature and magnitude of the intermolecular forces decide the structure of liquid and also its characteristic properties. Right? This also has to be noted that it may be noted that the nature and magnitude of intermolecular forces decide the structure of a liquid, and intermolecular forces and also its characteristic properties. Hmm? So let us understand some properties of the liquids. The first property which we are going to study is volume. Right? Volume. Unlike gases, liquid have a definite volume. Though they take the shape of the container, they maintain their volume. In liquids, the intermolecular forces are strong and therefore they do not expand to occupy all the available space as gases do. Therefore, a given mass of a liquid has fixed volume. For example, 100 centimeter cube of water always occupies 100 centimeter cube, whether it is placed in a beaker, a conical flask, or a large round bottom flask. Right? So let us write down, in liquids, the intermolecular forces are strong. The intermolecular forces are strong, right? And therefore they do not expand to occupy. They do not expand to occupy all the available space, right, as gases do. Right? For example, 100 centimeter cube of water always occupies 100 centimeter cube, whether it is placed in a beaker, a conical flask, or a large round bottom flask. The second one is the density. The molecules of liquid are more closely packed than gases, and the densities of liquid are more than the densities of gas. It has been found that the densities of liquid are about 1,000 times greater than the densities of gases under similar conditions. For example, the density of water at 100 degrees centigrade and 1 atmosphere is about 0.958 gram per centimeter cube, while the density of water vapor at the same temperature and pressure is about 0.000588 gram per centimeter cube. The higher densities of liquid than gases are due to the fact that the molecules of the liquid are more closely packed than gases. In general, the density of liquid decreases with increasing pressure. Okay? So it has been found that, let us write this down, that it has been found that it has been found that the densities of liquid are about 1,000 times greater than the densities of gases, than the densities of gases at under similar conditions. Under similar conditions, right? For example, the density of water at the density of water at 100 degrees centigrade and 1 atm is 0.958 gram per centimeter cube, while the density of water vapor at the same temperature and pressure at the same temperature and pressure is 0.000588 gram per centimeter cube. Okay? The higher densities of liquid, the higher densities of liquid than gases are due to the fact that molecules of liquid are more closely packed than gases, right? And hence, right, in general, another general observation is, in general, the density of liquid the density of liquid decreases with increasing temperature. Okay? The third point which we are going to study is compressibility. Liquids are much less compressible than gases. This is due to the fact that in comparison to gases, very little free space is available in case of liquid. Moreover, the repulsive forces between molecules prevent the compressibility of liquids. Therefore, a large pressure is needed to reduce the volume of liquid to a significant extent. For example, at 25 degrees centigrade, an increase in pressure from 1 atmosphere to 2 atmosphere decreases the volume of an ideal gas by about 50%, whereas the same change in pressure decreases the volume of water by only 0.0045%. Right? So liquids are less compressible than gases. This is due to the fact that in comparison to gases, very little space is free in case of liquids, right? Moreover, the repulsive forces between the molecules prevent the compressibility of liquid, compressibility of liquids, right? Therefore large pressure is needed. Large pressure is needed to reduce the volume of a liquid, to reduce the volume of a liquid to a significant extent. For example, at 25 degrees centigrade, an increase in pressure from 1 atmosphere to 2 atmosphere decreases the volume of an ideal gas by about 50%, whereas the same change in pressure decreases the volume of water by only 0.0045%, right? The next property is diffusion, right? Like gases, liquids also diffuse, but they diffuse slowly than gases. The diffusion of liquid is defined as the process of intermixing of the molecules of two or more liquids to form homogeneous mixture solution. Diffusion in liquids can be demonstrated, right? So let us write the diffusion of liquid. The diffusion of liquids is defined as the process of intermixing of the molecules of two or more liquids to form homogeneous mixture solution. Diffusion of liquid can be demonstrated by the following experiment. Put a few drops of blue ink in a beaker containing water. At first, a sharp boundary is observed between the ink and cloud. After some time, however, the blue color diffuses throughout the water. The rate of diffusion of liquid is much more slower than that of gas. This is because time taken for disappearance of the boundary in the above experiment is quite appreciable. On the other hand, when a drop of bromium is placed at the bottom of the container, it changes to vapor and immediately spreads throughout the container. Therefore, the diffusion in gases is very fast, right? In liquid states, the molecules are quite close to each other. Therefore, a molecule of liquid has to undergo a number of collisions with the neighboring molecules. Thus, there is more obstruction for the movement of the molecules of a liquid. As a result, the diffusion takes place slowly. In contrast, in gases, there is very less obstruction to the molecules moving because of the large empty spaces available for this movement. Moreover, in liquids, there are forces of attraction between individual molecules which tend to hold the molecules together. In other words, this slows down the process of diffusion. However, the rate of diffusion of a liquid can be increased by raising the temperature, which increases the kinetic energy of the molecules. Right? So, let us understand that. Try to answer why diffusion in liquids is of liquids, slower than that of gases. Okay? So the reason for this is in liquid state, the molecules are quite close to each other, right? Therefore, a molecule of liquid has to undergo a number of collisions with the neighboring molecules. Right? Thus, there is more obstruction. For the movement of molecules, of a liquid. As a result, the diffusion takes place slowly. In contrast, in gases, there is very less obstruction. To the moving molecules, because of large empty spaces available for their movement. Okay? Moreover, in liquids, there are forces of attraction between individual molecules, right, which tend to hold the molecules together. In other words, this slows down the process of diffusion. Okay? However, the rate of diffusion of a liquid, can be increased by raising the temperature, which increases the kinetic energy of the molecules. The kinetic energy of the molecules. Next property which we are going to study is evaporation. An important property of liquid is their tendency to evaporate. Though the molecules of the liquids are held together by attractive forces, yet they have a tendency to escape, which is known as evaporation. Thus, evaporation is defined as the process of conversion of liquid into its vapor at room temperature. So we can see that evaporation is defined as the process of the process of conversion of a liquid, conversion of a liquid, conversion of a liquid into its vapor at room temperature. Vapors at room temperature. Right? We know that when a liquid is placed in open vessel, it gradually evaporates and is converted into its vapor. For example, if we take some ether in a beaker, within a few minutes, the whole of it will evaporate. Now the question arises, how does evaporation occur? The molecules of the liquid escape from the surface of the liquid in spite of strong attractive forces among the molecules in the liquid. The process of evaporation can be explained on the basis of kinetic molecular theory as given below, right? So let us write this down, right? So explanation for the process of evaporation, for the process of evaporation based on kinetic molecular theory, kinetic molecular theory, right? As in gaseous state, all the molecules in the liquid state do not have the same speed, right? As in gaseous state, all the molecules in the liquid state, all the molecules in liquid state do not have the same speed, do not have the same speed, right? The Maxwell's law of distribution of speed of gases also holds good for liquid, right? The Maxwell's law of distribution of speeds of gases also holds true for liquid, right? Accordingly, different molecules in a liquid have different speeds and therefore have different kinetic energy, right? Accordingly, different molecules in a liquid, different molecules in the liquid have different speeds, and therefore have and therefore have different kinetic energies. Right? In order to understand this, let me drag a figure. Right? So this figure represents the distribution of molecular kinetic energies in liquid at two temperatures. Right? So this plot is for temperature T1 and this plot is for temperature T2, and it has to be noted that T2 is greater than T1. Right? So as the figure shows, the molecules have a distribution of kinetic energies, right? So y-axis is the fraction of the molecules having a given kinetic energy, and x-axis is the kinetic energy. So as the figure shows, the molecules have a distribution of kinetic energies ranging from very low values, right, to very high values, right? This portion. There is a certain fraction of the molecules at the surface which have very high kinetic energy, right? So the fraction of the molecules, if you look at y-axis, having kinetic energy very high is very less, right? This is shown in shaded area, right? So this is the area. These molecules can readily overcome the attractive forces in the liquids and escape from the liquid surface into vapors, right? So these molecules, the molecules which come in this category, they have the potential to overcome the attractive forces of the liquid and go into the vapor state. This process of escaping molecules from liquids to vapor state is called as evaporation, right? So let us move on to the next topic, which is cooling caused by evaporation, right? Cooling caused by evaporation. Cooling caused by evaporation. Cooling caused by evaporation. Cooling caused by evaporation. It may be noted that during the process of evaporation, cooling is always caused. This can be explained as during evaporation, the molecules of higher kinetic energy escape. The slow moving molecules are left behind, and therefore the average kinetic energy of the molecules left in the liquid state is lowered. Assuming that no heat is supplied from outside the source, the lowering of kinetic energy results in the temperature drop in the liquids, right? So let us write this down. It may be noted. It may be noted that during the process of evaporation, during the process of evaporation, cooling is always caused. Cooling is always caused. And this can be explained as during evaporation, the molecules of higher kinetic energy escape. The molecules of higher kinetic energy escapes, right? The slow moving molecules are left. The slow moving molecules are left behind, and therefore the average kinetic energy of the molecules, therefore the average, and therefore the average kinetic energy, average kinetic energy of the molecules left in the liquid state is lower. Left in the liquid state is lowered, right? Assuming that there is no heat supplied from the outside, right? Assuming that no heat is supplied from some outside source. Right? The lowering of the kinetic energy, the lowering of the kinetic energy results in temperature drop in the liquid. Results in temperature drop in the liquid, right? So let us now move on to the next part, which is factors affecting the rate of evaporation. The rate of evaporation. So the rate of evaporation depends upon three factors, which are: number one, the temperature. The second is strength of intermolecular forces. And the third is surface area. The rate of evaporation increases as the temperature of the liquid increases, right? So as T increases, rate of evaporation increases, right? For example, a glass of hot water evaporates more rapidly than a glass of cold water, right? As is clear from the figure which we have seen, the distribution shifts towards right, and the number of molecules having higher kinetic energy becomes more. Therefore, the rate of evaporation increases. The second factor which affects the rate of evaporation is the strength of intermolecular forces. The ease of evaporation of a liquid is related to the strength of attractive forces between the molecules in the liquid. For example, ether evaporates more rapidly than ethyl alcohol, while ethyl alcohol evaporates quicker than water. This is because the intermolecular attractive forces in these liquids are in the order of ether less than ethyl alcohol, which is less than water. So higher the intermolecular forces, lower is the rate of evaporation. So as strength increases, the rate of evaporation decreases. Rate of evaporation decreases. Right? The third factor which affects the rate of evaporation is the surface area. The greater the surface area to which liquid is exposed, the greater is the rate of evaporation. This is because greater surface area helps in escaping a large number of molecules from the surface. That means as surface area increases, the rate of evaporation increases. Right? So in this chapter, we have studied, so in this lecture, we have studied about the liquid state of matter, what are the liquids and how they are correlated between gases and soft gases and solids. Further, we have also seen the kinetic molecular model of liquids, and we have also studied the couple of properties of the liquid, right? Like for example, evaporation, volume, density, etc. In the next class, we are going to study some more properties of this liquid, such as enthalpy of vaporization, vapor pressure, and surface tension and viscosity, right? So I hope that you have enjoyed this class, and I hope to see you all again in the next class. Thank you.